Okay. So first question, gravitational field, STPM question 16. Okay, this is subjective question, section B. A satellite moves in a circular orbit at a speed of 4,400 meter per second. So determine the orbital period. So you are given the speed 4,400 meter per second. So we are going to find the period. Okay. So using the V and T, so what what formula to be used to determine the orbital period. Okay. So for orbital period, so you use circular motion lah. Use circular motion. Okay. So from the beginning, from F equals to ma, so the centripetal force here, the F here is the centripetal force, and the centripetal force is provided by the gravitational force. So it's gmm per r squared. And then the centripetal force equation, so we choose mv squared per r because v is given. So we cannot choose mv omega or mr omega squared. Okay, so we choose mv squared per r. Okay, next can cancel out the m. Okay, then cross multiply, so you get r equals to gm per v squared. Okay, so r is, okay, then to determine the period from the speed here given, so you use t equals to, say, one complete circle, for the circular motion of the satellite made is equals to 2 pi r. This is the circumference of a circle, 2 pi r. So divided by the speed, you get time. So the time taken is equals to the period because 2 pi r is a complete circle. Okay, so this is like speed equals to displacement or distance divided by velocity. Okay, so you use this one. Period equals to 2 pi r per v. Okay, then substitute the r into here. Gm per v squared. Okay, so you get 2.94 times 10 to the power of 4 seconds. So I didn't substitute 4,400 here. I skipped the step. But you all must substitute, okay? Don't leave the step. Substitution step. Okay, substitution step. Don't leave the substitution step. So must substitute 4,400 here. Okay, to get marks. Okay, then the answer is 2.94 times 10 to the power 4 second. Okay, so this is the answer for question 1A. Okay. Then question B. Okay, question B. A planet has radius of 5,000 kilometer. So this is radius. We use capital letter R because this is radius of the planet, not radius of the circular motion of an object like a satellite. The acceleration of free fall of the planet is 6.05 meter per second. So this is G. Determine the mass of the planet. So this is R, this is G. So how to relate G with R? So we use gravitational field strength equation. Okay. So because we are going to determine the mass of the planet, so G equals to G square root of Gm per R squared. Okay. Then you substitute the values of G here, 6.67 times 10 to the power of negative 11. Then M, G is 6.05. And the R is 5,000. Okay, don't forget to convert to meter. This is in kilometer. So convert to meter. So 5,000 times 10 to the power of 3. Okay, then bracket squared. So you cross multiply, you get M, the answer 2.27 times 10 to the power of 24 kilogram. Okay, so done mass for the planet. Next, escape velocity of the planet. Okay, how to determine the escape velocity of the planet? So for escape velocity of the planet, you use a principle of conservation of energy. Okay, use principle of conservation of energy. So it's 2 marks only. So you can directly use the equation for escape velocity. But just for revision, okay, so I start from the beginning again. Okay, so actually the escape velocity comes from the principle of conservation of energy. So you use total of energy here. Actually this step no need because the refer to the marks here is given is 2 marks only. So I just repeat from the beginning so that you can do in the maybe in essay question come out you can do. Okay, so total of initial energy plus total of final energy. So the energy involved only kinetic energy and potential energy. Okay, so kinetic energy initially is half mv squared and the v is equals to the escape velocity. Okay, the velocity needed at initial to project the object upward like a satellite, maybe using a rocket, so that it managed to free from the gravitational pull of the Earth. Okay, then plus the initial potential energy is negative gmm per r. R here is on the surface. So this is gravitational potential energy on the surface. Okay, don't forget to put the negative sign with the U, equation of the U. Then at final, at the peak, at the place where it free, the satellite free from gravitational pull of the Earth, the kinetic energy equals to 0. The gravitational potential energy also equals to 0. Okay, then you rearrange this, bring to the right side potential energy, so you get plus here. Then cancel out the m, so you get the escape velocity equation, square root of 2 gm per r. Okay, then the gm is you can substitute the 2gr at the on the surface. Okay, so the gravitational force gm per r squared is equals to mg. So cancel the m, you get gm equals to gr squared. So you substitute into the equation. So another equation for the escape velocity is square root of 2gr squared per r. Okay, then you substitute the values given here. So R is what? 5,000 kilometer, convert to meter, cancel one of the R here. Then 2gg is 6.05, substitute here. Then you square root, okay, you get 7.78 times 10 to the power of 3 meter per second. So I leave the substitution part, so you don't do that, okay. So in your working letter, in your assignment, you need to do later, you add in the substitution part, okay. So this is the final answer.
Teacher.
Yes.
We already found M right from B1. If I want to use M from B1, is that okay?
Can also. Can use 2 formulas here. Either this one or this one. Okay. So this one also comes from the G, right? This G 6.05. So it's okay. Okay. Any more problem?
Just a small question. Can you help a bit to explain the second step of the principle you just mentioned?
This one. Okay.
Yep.
So the initial total of energy means on the surface of the Earth example, we are going to launch the rocket so that it can exit the gravitational pull of the Earth, can go to the outer space. So the rocket will be launched at certain velocity, right? So that velocity must use escape velocity. So the velocity must be larger than escape velocity or at least equals to the escape velocity. Okay, so kinetic energy given on that launching moment must use this velocity, so is equals to half mv squared. Then plus the initial also involve potential energy. So the potential energy formula is negative gm per r. So generally is R, okay, measured from the center. So because it is on the surface of the Earth, so you substitute R. R is a radius of the Earth. Okay, so this is on the surface. Okay, initial on the surface. initial total energy on the surface. Then final total energy also involve potential energy and kinetic energy. So on the outer space there, for the rocket example just now, okay, to free from the gravitational pull of the Earth, so the kinetic energy will be zero. Okay, at the if it use escape velocity lah, if larger than the escape velocity, so the kinetic energy will have value, because it can continue move at the outer space there, where free from the gravitational pull of the Earth, like example Earth. Okay, so then if use escape velocity VE, then the kinetic energy just enough for the rocket to free from the gravitational pull of the Earth. That's why the kinetic energy final here is zero. Okay, understand this? And then plus the gravitational potential energy when the rocket free from the gravitational pull of the Earth is equals to zero also. Okay, so this is at the outer space once the rocket free from the gravitational pull of the Earth. Understand or not?
Teacher, just a small question,
Yeah.
but we will always have the gravitational potential energy, right? It will always be inverse to the distance from the center. It will only be zero at infinity, right, teacher? Or did I get the concept wrong?
Or the kinetic energy. You mean
No, potential, gravitational potential.
okay, this is gravitational potential energy. So at infinity, or at least at the point where it free from the gravitational pull of the Earth or the planet, the gravitational potential energy is zero. Is that what you mean?
Yeah, because it will
Yeah.
always have value, right? But the value is like inversely getting smaller, smaller, smaller. It will only be zero at infinity, right? So we are assuming the escape velocity will bring it to infinity, is it?
Yes. When you bring to infinity, it's considered zero. Okay, it's considered zero, the gravitational potential energy. Once it's free from gravitational pull of the Earth, okay, considered zero already.
Oh,
Mm.
okay, okay. I'll try understand a bit.
Okay. From the formula, okay, here GMM per R, small letter R lah for the gravitational potential energy. So as the R increasing, the U decreasing. So it will decreasing until it's approaching to zero. So at infinity, we consider as zero lah. Yeah? Okay. Okay, if no more problem, we go to the next question. Yeah? Okay, so next question is satellite motion in a circular orbit. Okay, define Newton's law of universal gravitation. Okay, so this one just use gravitational force between the two masses is directly proportional to the product of the two masses and inversely proportional to the square of their separation. Okay. If you want to write in the mathematical form, can also, but you must define all the mentioned variable. Okay. So 1 mark only. So B, a satellite is orbiting the Earth in a circular orbit. So derive the relationship between the period T and the radius of the orbit R. So between period and the radius T and R, okay, T and R. So for to find the period, so you use circular motion, okay, centripetal force, circular motion concept in chapter 5. Okay, so the centripetal force generally is F equals to ma. So F is centripetal force and A is for the centripetal acceleration. Okay, so centripetal force is provided by the gravitational force gm per r squared. And then the A is a centripetal acceleration, so you substitute r omega squared. So we use mr omega squared because omega is related to period by the equation omega equals to 2 pi per t. So that's why we use this one mr omega squared. And you see the marks here, the mark is 5 marks. So you must start from the beginning. Okay, so start from the centripetal force, okay, concept in the circular motion. Okay, next we cancel out M. You get okay, haven't cancelled out, but you cancel out earlier. So substitute the omega equals to 2 pi per t. Don't forget the squared. So you cross multiply, cancel the m just now. So t squared is 4 pi r cube, cross multiply here, r times r squared. So 4r cube pi squared per gm. Okay, so per gm. So you must use the r here given, radius of the orbit, capital letter R. But I think this is typing error in that book, supposed to be small letter R. But it's okay, we just follow. If the question gives capital letter R for radius of the orbit, so you use R. I just want you all to be careful. Whatever symbol given in the question, use that symbol. Don't use other symbol. Okay, so maybe in this question, some of you will use small letter R. So be careful lah. Given here capital letter, right? Okay. So you use capital letter. So this time the capital letter is not refer to the radius of the planet. This is radius of the orbit. Okay, understand or not? Okay, hopefully you understand. Then okay, now sorry. Okay, done the question. So
Okay.
yeah.
I think the final answer should be square root, right? Because you want to leave.
Continue lah. You continue. T equals to square root of 4r cube pi squared per gm. Okay.
Okay. Thank you.
Okay. So you continue to simplify this equation because of the squared here. Okay. Any more question? No more. Okay. So we have derived the relationship between period and R. Okay. T and R. Okay, if no other question, we go to C, 1C. Okay, for 1C, a satellite with a mass 1,337 kilogram, okay, mass, is initially orbiting the planet Mars at an altitude. Okay, be careful here, altitude. If you meet this word, altitude is measured from where? From the surface of the planet, planet Mars, not from the center. So must be very careful. Altitude of 45,000 kilometer. Okay, gradually descending to a lower altitude, 316 kilometer above the surface of the planet Mars. So calculate the potential energy of the satellite at the initial altitude. So 3 marks. So you are given the initial height, okay, measured from the surface. Okay, remember it's altitude. Okay, then the descending to a lower altitude. So this will be the final height, final height. Okay. And below the question given the radius of the mass, 3.39 plus times 10 to the power 6 meter. So to measure the distance from the center of the earth, so the h there must be plus 2r. And then the mass of the planet is 6.42 times 10 to the power 23 kilogram. Okay, so the question asks for potential energy. So potential energy formula is U equals to negative gmm per r squared. So this is the general equation for potential energy. But the question asks only the potential energy at initial altitude. Okay, initial altitude. So initial altitude is 45,000 kilometer. Okay, so the 45,000 kilometer convert to meter. Don't forget to plus the height, the altitude 3.39, initial altitude 3.39 times 10 to the power of 6. Bracket square. Sorry, this is okay. This is radius. Sorry, initial altitude is 45,000 times 10 to the power of 3. Radius of the Earth. Sorry again, altitude, okay, height from the surface plus the radius of the Earth, 3.39 times 10 to the power 6. Okay, always measure R from the center of the planet. Okay, this is what common mistake student makes. Forgot to plus the radius of the planet for the R. Okay, for the R. Okay, then square here. Don't forget. Also, many common mistakes student makes from here. Okay, the rest is substituting the G and then the mass of the planet and then the mass of the satellite. Oh, okay, satellite, correct. Okay. See, then you get the answer. Negative 1.18 times 10 to the power of 9 joule. Okay, another common mistake student forgot is to just substitute the sign together in the gravitational potential energy. Okay, that is C1. Then we go to C2. Calculate the change in energy of the satellite during the descent. Okay, during the descent. So change in energy. Okay, the word change in means final minus initial. Final minus initial. So the energy we use here is total energy. Okay, total energy. Okay, what is meant in this question is total energy, kinetic and potential. So the change in energy will be total energy final minus total energy initial. Okay, so what is the equation for total energy? Can remember or not? We've done before. Okay, so the total energy is negative GMM per 2R. Okay, GMM per 2R. So you substitute into here. Don't forget negative. For total energy got negative. So it's similar to the kinetic energy. Kinetic energy also GMM per 2R, but kinetic energy don't have negative sign. Okay, for total energy, GMM per 2R got negative sign. Okay, so you must memorize the formula for kinetic energy, potential energy, and gravitational potential energy. Okay, so for the final and total energy is negative GMM per 2R. So minus here and then this one minus again. So you will get plus negative GMM per 2RF plus GMM per 2R. This is where the student always make mistake with the sign. So here plus, okay, or you can rearrange the equation. This one bring to the front also can, or remain like this again. It's up to you lah. The same thing. The two expressions is the same thing. Okay, now substitution part. Okay, substitution part. So you can use this method also. Instead of substitution part, you substitute twice. You can factor out GMM per 2. GMM per 2 factor out. So in bracket becomes 1 per R1 minus 1 per RF. Okay, like this also can. If you use here, you need to substitute the value of GMM twice. So if you use factorization, so you just need to substitute once only. Okay, now substitute the value here, GMM per 2. So G M mass of the satellite and mass of the planet mass divided by 2. And then in bracket here is 1 per R1 and minus 1 per RF. So don't forget the R must plus the radius, the altitude plus the radius. So altitude initial is at 45,000 kilometer convert to meter plus the radius of the planet mass. Okay, for RF also do the same. Radius, altitude, okay, altitude, second altitude, okay, convert to meter plus the radius of the planet. So always be careful. Radius is measured from the center of the planet. Okay, so the answer, I straight away go to the answer. Okay, so negative 7.13 times 10 to the power of 9 joule. So you get negative. Okay, negative. So negative means it decrease. Okay, decrease in energy. Okay, so the question that didn't ask for that, but it is understood that negative here means decrease in total energy. Okay, any question in C2? So it's 3 marks only. Okay, 3 marks is for the answer and then the substitution and for the equation here. Okay, so equation here all considered the same lah. Okay, all considered the same. Okay, so if no question, we can proceed to question C3. Okay, question C3. Orbital speed of the satellite after descending to altitude 316 kilometer, 316 kilometer. So the speed. So for orbital speed, okay, you use circular motion concept. Okay, so you use centripetal force is provided by the gravitational force. Okay, so centripetal force is provided by the gravitational force, gmm per r squared. Then the A here, which one to be used? mv squared per r, mr omega squared, or mv omega? So we use to find the speed, so we use mv squared per r. Okay, so because we want to find v. And then omega angular velocity is not given here. So we use this one instead. So you cancel the m and one of the r cancel out. So you get v equals to square root of gm per r. Okay, then substitution part. Okay, gm. Okay, this again we meet r always measured from the center of the planet. So the altitude plus the radius of the planet. Okay, don't forget this. Okay, so you get the answer 3.40 times 10 to the power of 3 meter per second. So this is the answer for number 3. Okay.
Teacher,
Yes.
can you explain again the first line, like how you get the square of gm per r?
This one.
How you from f equals ma?
Start from here. So this one, you use gravitational. I mean centripetal. Centripetal force. Okay, use circular motion concept. So the centripetal force here is given by the or supplied by the gravitational force. So that's why you substitute gmm per r squared. So the satellite now. Okay, the satellite move in circular motion around the planet using this force, okay, because of this centripetal force, gmm per r squared, then equals to the ma. So in circular motion, there are 3 equations. We can use mv omega, mv squared per r, or mr omega squared. So to determine period, you use mr omega squared. To determine the speed of the satellite, you use mv squared per r. Okay, so that's why we use this one for the right side of the equation. So becomes mv squared per r. Okay, then you equate this, then simplify lah. Cancel m and then cancel r, one of the r here. So becomes gm per r. Okay, gm per r. So the v squared, the squared here, so becomes square root lah. So that's why v equals to square root of gm per r. Okay,
Okay. I see. Thanks.
Okay. Okay, then this one okay. So any more problem for question C1, C3? No, Okay, so if no, we go to the next question. So next question, question 2. Question 19, also essay question, altogether 15 marks. 4 plus 3 plus 4 plus 2 plus 2, so 15 marks altogether. So number 2A1, explain the condition when a body which is in motion can have a change in velocity and at the same time have constant acceleration. Okay, so why a body, example the satellite, okay, in a circular orbit, okay, has can have a change in velocity. So in circular motion, it has a change in velocity because the velocity always change direction. Okay, change in velocity means change in direction with the same what do you call that? Same value, okay, same value, same magnitude, same magnitude, but different direction also considered as change in velocity. Okay, then constant acceleration. Okay, constant acceleration. So when a body exhibits circular motion, it moves with constant speed, okay, but different velocity. So what does it mean by different velocity? Because it change in direction. Okay, change in direction with the same magnitude speed. Okay, it has a constant acceleration because it is acted by a constant centripetal force. So in the case of satellite motion in circular orbit, it is equals to gm per r squared. So it depends on the case. Okay, for other case like the string move attach object attached to a string, so you move it in circular motion, so it's given by the what you call that tension in the spring. Okay, and can be given by the supplied by the normal force and also mg. Okay, so in this chapter the centripetal force is provided by the gravitational force. Okay, this is what is meant by the constant centripetal force. Okay, which is directed towards the center. So this is the condition for the body. Okay, which is in motion, in the circular motion. Okay, then number 2, derive the relationship between the velocity and acceleration. Okay, so from the 2a1, so we are going to derive the v and a. Okay, v and a. So we use chapter 5, okay, chapter 5 to derive 2a2 because the satellite also move in a circular motion. Okay, now so we are going to derive the relationship between v and a. So we start with the circle, okay, to show the path for the circular motion of the satellite. So let's say the satellite move from here to here, okay, from here to here. So the distance of the satellite from the center of the circular motion is given by this radius, and the angle is given by the d theta. Okay, so we use a vector to we use vector diagram. So this 2v, okay, this is direction of the speed. Okay, so we use we dot vector diagram without changing the direction. Okay, if the direction this way, so you follow this way. Here this way, you follow opposite. So why opposite? Because we are going to find the change in velocity. So the change velocity will be in this direction. Okay, so let's substitute the value. This is V1. Okay, this is V2. Okay, the final position. So this is V negative V1. This is V2. So when you use vector diagram, okay, sum of the vector is V2 minus V1 will give you a change in velocity, which is dV. Okay. So for a small angle, delta B, but for mathematical solution later, approximation value for a small angle we use D. D. So dV equals to V2 minus V1. This is change in velocity. So now we are going to relate this change in velocity with the acceleration. Okay, acceleration, because acceleration is change in velocity per time, or another word, acceleration is rate of change of velocity. Okay, so we got a change in velocity already. So now we use this is a circle. Okay, so we can use from the maths s equals to r theta, and then the angle is same lah, d theta. Okay, you transfer this form to vector form. Okay, so the angle must be the same, and then this triangle form is the same as the triangle form here. Okay, it's the similar triangle. Okay, then from the maths equation s equals to r theta. So for this one, okay, we use this one. The arc of the circle here is ds. Okay, it's a small changes of arc, so we use ds. Ds. So equals to r, radius of the circular motion r, and then times the theta. So the theta is a small angle, so we use d theta. Okay, so d theta means small angle. Okay, now to relate with velocity, so you per time both side, so you get ds by dt, this is velocity lah. Okay, velocity, and then d theta by dt is angular velocity. So angular velocity is equals to angular displacement divided by time. So r omega. So now we get v equals to r omega. So we do this expression. Okay, we refer to the circle here. We refer to the circle here. Okay, next we are going to refer to the vector diagram. So vector diagram also we use the same s equal to r theta. Okay, so because of the small, very small, what you call this, very small angle, small angle, so we can use the dv here using s equals to r theta. So therefore dv equals to r, it becomes v because the length of the vector represent in here is v. Okay, so v1 is equals to v2, so we use v because they are same speed. Okay, same speed. So dv equals to v d theta. Okay, here dv equals to v d theta. So we use s equals to r theta for the vector diagram here. Okay, then we divide both side by dt, so we get acceleration. So dv by dt is acceleration, d theta by dt again is the angular velocity. Okay, we remain the same here. Okay, now combine these two. Combine these two. We substitute omega equals to v per r into the equation. So we get a equals to v squared per r. So this means we have derived, here derive the relationship between velocity and acceleration. So in this expression, we have a and we have v. We have acceleration and we have velocity. So means this is the final answer. Okay, derived already. Okay, any question for this question? Okay, 2A2. Understand or not? Okay, the steps actually given in the PowerPoint notes, in the circular motion PowerPoint notes. So okay, you can refer there. So this come out in the past year's question. So A is equals to V squared per R. So if you substitute it into M equals to MA, so becomes MV squared per R. Okay, this is where the centripetal force equals to MV squared per R comes from. Okay, so silent means understood. We go to the next question, 2B1. Okay. A communication satellite orbits the Earth at a fixed distance h from the surface of the Earth. Again, you see here, h from what? From where? From the surface of the Earth, with a speed of 6,500 meters per second. Okay, so you are going to calculate the h to be 1. Okay, so to calculate the h is from center of the surface. Sorry, from the surface. H is measured from the surface of the Earth. So you must plus the r, radius of the Earth. Okay, so from, wait, calculate. Okay, so the satellite orbits the Earth. The Earth. So that's mean you need to use the centripetal. You need to use the circular motion. Okay, circular motion concept where force is provided by the gravitational force, gmm per r squared. And again here, A, we use v squared per r. Okay, why? Because the speed is given. Okay, speed is given. So that's why we choose a v squared per r. We didn't choose v omega, or we didn't choose mr omega squared. Okay, now cancel the m, cancel the r. We get v equals to square root of gm per r. Okay, now we substitute the value of speed 6500. Okay, the g, then the mass of the planet Earth, mass of the planet Earth, not given here, but you can get it from the booklet, from the booklet given you during your exam lah. In your exam, you are given a booklet. Okay, so the booklet all has the values, constant values inside there. So if not get from the inside there, they will give here lah, but here not given. So I think in the booklet got Then the radius means the h plus the radius of the earth. Okay, so radius of the earth in the booklet is given by 6.38 times 10 to the 6. Okay, plus h. So don't worry lah about this one not given. So in this question, okay, luckily it's not given, so I mention you right now. So always refer to the booklet given, if not given the constant in the question. Okay, so 5.97 times 10 to the 24 is the mass of the earth, and 6.38 times 10 to the 6 is the radius of the earth. Okay, plus the h. Then you simplify this equation, becomes h. I go straight to the final answer. Okay, go straight to final answer. H is 3.04 times 10 to the 6 meter. So any problem or not in this B1? It's the same question as the previous question, right? So you see the question here, H is 4 marks. So if 4 marks, okay, if 4 marks, so that's mean you need to get the answer, the substitution and the equation. So the equation must be start from here lah. Okay, start from here because 4 marks. So always refer, like I said just now, always refers to the what marks given. Okay. So you cannot maybe these 4 marks you cannot start straight from the formula for the speed here. Okay. So start from here. To be safe, start from here. Because it's a large mark, quite a large marks here, 4 marks.
Teacher, this is the same question as we discussed before, right?
Yes, but this
okay.
4 marks, right? 4 marks.
Okay, teacher.
Okay. So refer to the marks, even though some question is same as the previous question, but always refer to the marks. So for the 4 marks, you as a guideline, which step to be safe, start from the beginning here. Okay, then B2. Okay, B2 determine the period of the satellite. So the period of the satellite, so we use same circular motion, but this time use mr omega squared. Okay, here. But now you see the marks here, the mark is 2 marks only. So if the 2 marks only, you can straight away use the formula T equals to 2 pi square root of the square root of I forgot the equation. But if you use this one, okay, so you get similar to the previous question. So I just go straight to the final answer. So you get this, right? So you get this equation. If not, you use 2 pi r per v also can. 2 pi r per v also can. You will get same answer. So if you use this one, okay, so substitute the values of radius measured from the center. So you need to plus the h. Okay, g value, m value. Okay, pi is 3.142. So the square root of this one, you get t equals to 9106 second. Or you can use 2 pi r for one complete circle in the previous slide, in the previous question, 2 pi r per v. Okay, v is given here. Okay, that's why it's 2 marks here. Okay, 2 marks because v is given, so it's very easy. So you just use 2 pi r per v. If you use this also can still get full marks, 2 marks, but it's a longer method, longer step. Okay, any question or not? Understand to B2? And then the second step, understand or not? Use 2 pi r per v. I didn't show here. Okay, use 2 pi r per v. Also, you get t equals to 9106. Okay, if no...
Teacher,
yeah.
The small sigma 2 pi over t, can I substitute that only if the question say does a full rotation? if let's say they say like only at a half rotation or whatever, do I have to change the radian also?
For MR omega. MR
Yep.
omega, omega is 2 pi per t, so the t must always a period. One complete time taken for one complete circle.
If they ask like a half time taken for half or quarter or
Cannot
less
use
than
time. The T stands for, okay, represent the period. So cannot use time for half rotation or whatever. So must use period means time taken for one complete rotation. Okay?
if I change the what radian teacher like 2 pi means 360 degrees, right? So they say like only half for the rotation. I want to find the period for half the rotation. If I just use pi,
If you
is
want
that
to
like
find
possible?
if you want to find the period from there, okay, but it's still period. Okay, still period because it moves with the constant angular velocity. So even though you are given for a certain angle, okay, the time taken for certain angle, so you can find for half to pi radian lah, right? For the t period, can also. But you must understand that t stands for period. Okay, calculate the period first. Cannot straight away use the time given for certain angle.
Oh, okay, understood.
Okay. So the last question, 2C, why the satellite in B, okay, can stay in orbit during its lifespan? Okay, so it can stay in the orbit. So the 2C, two marks here. 2 marks, you must have two contents. Okay, two contents. So the first content, the satellite will move in a circular orbit around the Earth because the gravitational attractive force between the satellite and the Earth acts as a centripetal force. So another word is the centripetal force is provided by the gravitational force. Okay, gravitational force for the circular motion. Okay, so mention about the centripetal force. Then the second content is the satellite move at a certain speed. Okay, certain speed which has a constant magnitude to keep the Earth satellite distance. Okay, this is another content. Okay, so 2 marks. 2 marks, make sure 2 contents. Okay. This one actually comes from here, V and R. Okay, V and R. So it moves with the certain speed to keep the Earth's satellite distance. So R change, okay, R change, then V. So this one, GMM per R squared, explained by the first statement here. Okay, this is centripetal force, and then this one is a gravitational force provided. Centripetal force provided by the gravitational force. Okay, the first part. The second part, okay, second content comes from this one, mv squared per r. So with the constant speed, okay, to get the Earth satellite distance, to keep the Earth satellite distance r here. Okay, so that's the 2 points for question C. Okay, question C. So any question on 2C? Okay, Kenneth. Okay, so that's all for today.